Welcome to another session, Data with Nick the Greek. Today we're gonna continue our discovering journey to understand and see how the Spark partitions during loading of data really behave and really deep dive into the secrets and our influence factors which we identified the last time. So just to shortly sum up again why we're actually doing it. So first of all, it's important to understand how Spark-based partitioning influences them based on different factors and to really be able to improve the performance, understand the performance, debug better. You also learned the influence of the partitions already. So empty partitions are non-optimal because the scheduler just schedules empty data around. Also, this distribution of the data is important. And lastly, if you can influence the number of partitions already doing loading, we don't need to execute coalesced or especially partitioning, which is a very expensive operation, as you already know, um, after loading the data during the transformation phase. And with that, let's get started. So as always, we are setting up our Spark session. In this case, I already have done it. And we have multiple functions where we do some analysis. That's something you can just have a look afterwards into the GitHub code if you're more interested, like how exactly those functions have been coded. So what we learned already in the previous sessions, that we have mainly 6 influence factors: the number of cores, the file size, the number of Parquet files, the row groups in the Parquet file, which is still not gonna have a look today, the max partition size, and the max cost per byte, which basically estimates the cost to open a file. And that's something we're gonna see also today a little bit how the behavior is, because basically by adding like cost additionally, it avoids putting like too many data into one partition. And as we now have created last time a really nice algorithm, so today we're really gonna use this algorithm to exactly analyze the behavior of 5 of those 6 influence factors. And just have a repetition. Let's see what we did the last time. So how does the final algorithm look like? So in this case, we loaded, let's wait a second for this to execute. So in this case, we loaded a file with a Parquet file with 8 snappy Parquet files and a row count of, let us count, 64 million. And here we can basically see the snappy Parquet files, so each is 64.9 megabytes big. And you can also see it in the file analysis. So 8 files, 64 megabytes, 518.9 megabytes total size. Similar to the row count. And we're setting our default configuration. So in this case, we're going with a max partition size of 128 megabytes, and the min partitions as the number of cores, which we have 4, and also the open cores is the default parameter. So really default configuration just for our short demonstration. Then the next step, what we're doing is we calculate our max partition size. And this max partition size is really the basis, which depends, as we already know, based on the open cost, the minimum number of partitions, and the max partition bytes. So really, we are creating here like a minimum between max partition bytes and the size per core padded. Or if you have really small files, it's something we're gonna see in the next session, when open cost in bytes might also become the limit of a partition. So basically, that's like the final calculated value how the partition size is basically really cut off. So by running here, we can see in this case we are getting a padded file size of 526 megabytes. The size per core is 131. This is bigger than the max partition size. And that's why the max partition or max split bytes in this case is also 128 based on our configuration. Then what we're just doing here is we're getting the data. So basically this column here is a list, because we need only the list of the values. And then we have this splitting algorithm. And I adjusted it a little bit. So in the last session, we just received a list of the files. So basically, based on the max split bytes, this function is splitting them in pieces. So you can see it here. If the remaining, so file size minus max split bytes, is still big, bigger than 0, is also bigger than max split bytes, we're gonna cut them into pieces based on the max split bytes. Otherwise, only the rest gonna be given out. And in this case, as we said, we have 128 megabytes, and well, as all our files are lower than 128 megabytes, of course the length is not split it down. But if you would have smaller lengths, please check the previous video, the episode 7 for the algorithm. You're gonna see, okay, they're gonna split it further down. So in this case, we have 8 files as expected, because we didn't really have a split. Then the next thing what we're doing is we are trying to put as many files as possible into one partition. So roughly the algorithm, what it's doing is it checks the file size is bigger than the max bit bytes. Okay, we close the partition, open another one. And here we now get a dictionary, which basically includes all the files which are added to it. And the important thing is we have now the length. So that's basically the simulated length of one partition, and then also actually the file size. So the length is basically used for the algorithm to create those partitions which we don't like for Parquet files, those empty ones. Exactly. And then we have our function will basically check what is the actual number of partitions and how the number of bytes, so what's the size within one partition. So we see it's also 8, because here we had eight calculated partitions. And then lastly, I just created an algorithm to do some analytics on it, which we're gonna use now for further analysis. So basically, first of all, we get this table, so we just aggregate it and explode it. So we now see the partitions we have and the length and file size of each partition. And then if you're gonna have a look on the previous table, you pretty much see that the compressed bytes here is exactly the same as the file size here. So it just shows that the algorithm which we developed actually really works well. Exactly, and at the end, based on the file size, we just do some analytics. So I calculate the max size, the min size, the median size in bytes right now, but we can also calculate megabytes. We're gonna do it later, so that we can see not only the number of partitions, but really how the data size behaves within each configuration. So as mentioned, empty partitions is not good, so we can see it here. And also, like, we want to try to have like a uniform data size, and that's how we're gonna choose which configurations are the best ones. And with that said, let's jump into our first simulation. So in this case, we're gonna simulate one of the most important values, the max partition bytes. And let's see how it behaves over those parameters. So 5, 10, 15, until 1024. And so we are not running this together now, but basically what I'm getting as an output is this following table. So we have the file size in megabyte, which we simulated and defined here. Then we have the number of files, also 20. Then we have the average size, which is 51.2 megabytes. Then the number of cores, which is also static. So those four input parameters we haven't influenced right now. And then we have the max partition bytes, or MB in this case. So we just go up from 5 to 1024. And let's have a look what's happening here in the background. So first of all, the number of partitions for small for a small value of math partition in B is really cut off, because if this value is small and this value becomes also small, because as you can see here, the size per core padded is 276, and so this is going to be always the value. That means everything regarding max partition size, which is smaller than that value, gonna basically cut something off. So you can see here, once it becomes once it becomes above 276, so 512 in this case, you see it's not taking the max partition bytes anymore. For us, what it means, the small values cut the data so much off that we have a lot of empty partitions, because we have only 20 files, meaning here you always see the difference. It just has 60, 20 empty partitions here as well. And then only once we increase the value, in this case, to 60 megabytes, which are above the average size, we see, okay, the max partitions disappear. And then now here's like the area actually where we would like to choose the optimal number of configuration. So one area is here with 20. So we can see, okay, here we have highly distributed data. It's dividable by our number of cores. 10 has the issue, even if the data is well distributed, that we gonna have like two partitions which gonna be running in the third round, meaning two cores gonna be empty running, because we have 4 cores, then first 4 partitions, second 4 partitions, 2 left. So there are also like circumstances where you have smaller files where it doesn't make a big difference. But here we would have 120 megabytes just running with 50% of the capacities we already have. Another way is, even if we said, okay, factor 2 usually, but the size of the data can be also still okay if you don't have too many shuffle operations afterwards, or any shuffle operation. You can see here you have equal to the number of cores. We have a very distributed data set, and that's like the logic way you can go through. So this could be a little bit more risky, because it goes already a little bit higher, but still on a okayish level with the partition size. And here you are probably more secure, but could have a little bit too much of scheduler overhead. That's something we're gonna just give it a try with different configuration with a real data set. Now let's do exactly the same, just with the number of files. So we are doing some experiments with 1, 4, 5, 8, etc. until 1024 number of files with the same size. So our size is gonna stay always 1024 megabytes. And what we're doing is we just increase the number of files. And the first thing what I want to say is we can have a look on those values, but let's ignore them. So I'm already telling a secret, because we said we are not considering the the blocks or row groups within Parquet files. But the actual thing is, if you would run this and check what's the actual size for such a file, you might see a different behavior. So what's basically happening is Parquet files create 128 megabytes row groups as a max, and those are actually splittable even if you have one snappy Parquet file. Just the splitting works totally different. That's why I want to exclude this algorithm to a later stage. So let's start looking on here. So we have and by the way, one thing I want to mention, I mentioned 128 megabytes, and you see also the default value of max partition bytes is 128 megabytes. So I assume this is one of the reasons that the value is set to there, and that's also one of the reasons that you should be careful if you're gonna reduce it, especially significantly. Not only the empty partitions which are generated, which we saw. But if you have bigger paquet files and then the snappy paquet files also bigger, the 128 megabytes, I'm not sure if I necessarily would reduce significantly. We're gonna see later how this behavior really looks like. Okay, so if we increase the number of files, what we can see is the average size of a file becomes smaller. So until 128 megabytes, we have, for instance, here like a good scenario where we can get 8 partitions perfectly. I mean, we have 8 files and they're 128 megabytes, so that's like a good one to really work with. Let's see if we have a scenario where we don't have um, a, a good circumstance. So first of all, what's also good is the number of empty partitions is quite small. So we can see that this value seems to have like a bigger influence. Like the number of files doesn't really at least influence the number of empty partitions. What it influences is definitely the overhead. So you cannot see it here in the table, but if you are gonna be looking like on the cost of bytes, you're gonna see the size per core padded is becoming no, here 5,000 is becoming quite big, and our size per core padded is equivalently also big because it's like divided by 4 our number of partitions, and that means basically our max partition size is always the smallest value here. So basically, that's why you see also that the delimiter here is always 128 megabytes, and you already guessed it. Like if file size 1024 divided by the number of cores is already 256, then of course whatever comes afterwards, due to the padding, due to the 4 megabytes per file added, this gonna be here always our influence. So that's also the reason that we have like basically no empty partitions here. Looking on here, so we see some interesting things. So here, for instance, we have some distributions, so we would have to take now a little bit into detail why this happened. Here we have a uniform distribution, but we have again the problem with the 10 partitions. So two partitions gotta be running alone with 2 cores not doing anything. But here we have a good one. So here we can see, okay, number of partitions 12. We have a well-distributed data set, and it's dividable by 4. So that's probably here again. That's probably something I would go, or this one here with 128 megabytes each. So those would be probably the 2 ones which are feasible. Here we have another 16 with 64 megabytes, but this size of data actually, 8 partitions, 128 megabytes sounds really good. So in short, we saw that number of files really can, so the number of files can really change your distribution. Also, what to say is in reality, we saw it above, you usually have always a small variance of the size of each snappy file. So it's not always exactly the same as we did here now in the simulation. So this might in the real scenario also have some slight behavior changes of the number of partitions, as really the calculation is being done in bytes in the background. All right, now let's do the next experiment, and this one gonna be an interesting one because we're gonna see how the open costs behave. So in this case, we are not touching the number of files, so we keep them static, 20 files, but we are slowly increasing the total file size. So let's have a look into the experiment. And this time I would like to start from below. So as mentioned, this one, let's ignore it because the average size is above 128 megabytes. But what we can see here again is as well. The average size, the padded size per core, I needed a second to get me, is bigger than 128 megabytes. Here in the beginning, it's just delimited, delim the delimiter is there, but then at some point our file size becomes so small that actually our padded file size per core is basically the limit for the partitions later on. Interestingly, we see empty partitions known, so that's already good. The number of partitions is 4, and that's actually rather the interesting aspect of open cores, which we can see now. So we see that the average size of files becomes here below 4. And what open cost bytes is doing, we can best see it here. So you have a file which is a few kilobytes big. No, this one probably even bytes. Maybe what is 1000 of 1 megabyte, 100 bytes, if I calculate correctly. And so basically what happens roughly is the open cores make the file basically not 100 bytes, but it makes it roughly 4 megabytes big. And that means if we would have not the open cost, it would be a small file, and our delimiting max split bytes is 20 megabytes. But basically what would happen, it would put all the files, all the 20 files into one partition. And that's why in our documentation or definition, let's call shortly up, it states is the estimated cost to open a file. So basically, Spark is stating opening a file has a cost. And if there's not much data into it, I have to open a lot of files if I have a very small files to get the same data as if I would have a big file. And that's basically the cost of it. So, and by this simulated cost, it just limits the number of files, small files in this case. Let's go back to our experiment, which are getting into one partition. So if you have a big file, it just takes the one. If you have a lot of small files, it tries to limit the number of files. Even here with 1 megabyte, we set our max partition to 128. Theoretically, could even go up to there, but basically it's limiting it down already with the max split bytes to 20. And then at the end, we're gonna see, okay, we have 0.3 megabyte here. So that means, well, how many files do we have? 4. That means, yeah, roughly 5 files have been added there. Yeah, so it's, yeah, this huge because it's 0.05 times 5 is 0.25, and then here we just round it up. So that's basically about well, smaller file problem and the file size megabyte. And I mean, you can see that we said like 2 small partitions are not always good. But I mean, if you really have like small files, 4 like that is definitely better than having like one partition with all the files. There you might have potentially also scheduler, or at least I assume the Spark query optimizer would have issues to load all the data in. So this behavior here with 4 partitions is probably the best one if you can like reorganize your data better, even if, well, the file size you cannot influence, but the average file size based on the number of files. So we could at least go down with the number of files here to just generate bigger files. So now let's simulate the open cost. I can tell you as we do this here with the standard parameter, it just really doesn't have any influence because the the open course only becomes active if we really have, well, under special conditions, small files. That's something we gotta deep dive next time, because basically you can adjust the formula, realize, okay, first of all, you need a smaller file than open course bytes, and the number of files have to be smaller than the number of cores. Then the open course really gonna become the max bit bytes. But independent of it, you saw that with the small files, you really see how the open course behaves. And now that our average size is always the same, with this size, the open course doesn't have an influence. So we're gonna repeat this experiment with smaller real data sets, and then we're really gonna see, okay, what's the behavior similar to what you saw here already. So, and the last experience we gotta look on is the min partitions, which basically is the number of cores we have. So in our case, we had 4 cores, but let's see how it behaves if we change the number of cores. So first of all, here we have one core, and okay, that's interesting. No, it's not interesting. I was just looking on the 1024 megabytes, but we have 51.2 megabyte files, and what it generates here is 10 megabyte files. Cores we have the 128 megabyte limitation. So even if you have one core, it does exactly the same. Cores or max partitions and the padded bytes per core is basically below 128 megabytes. And as we know, it takes the minimum. So now we reach the point where basically the delimiter is not the 128 megabytes, because now we divide, roughly said, 1024 plus 4 times 20 divided by the number of cores 10. So it's 110.4. Well, of course, I see it here. I cannot calculate it by myself. And yeah, then this is the limit of the files, but 51.2 times 2, which is 103.4, is still smaller than this size, so it doesn't change anything. But here we're gonna see the influence now of the number of cores. And so, well, again, repeating here, it's divided by 4, so most probably I would go with that. Hopefully not too much overhead regarding the scheduler. But later on, I mean, you can guess it if you have 20 files and we have 24 partitions or 28, no, not partitions, cores, those cores just stay empty. So so this would be equivalent on oversizing your machine for your data size. So this goes also into the direction. Choose a machine which is needed for your size of the data. Don't let the performance availability is just lying around there. So here you want maybe to go with a 12 core machine, because here we have like nicely 20 partitions, 50 and a good distribution. Now, okay, yeah, that's actually a good point. We have to consider also the number of cores. I just failed by myself nearly. So here you have 12 cores and you have 20 partitions. That means in the first round, 12 gonna be used. In the second round, 8. So sorry for this error, because we are changing the number of cores. So the best one you can do is, as we said, we want to take a number of partitions which is divisible of a number of cores. And the only good values I see here is 10. So 10 number of cores, 10 partitions. So you're going to have one round. We said we want to have a factor of 2 to 3 usually, but it's still, I would say, acceptable with 102.4. The other option is, but here you would have 5 rounds, would be going with 2 cores. And then you're going to have 5 rounds of 102.4 megabytes. And yeah, I hope those examples which we did, so that's pretty much it, helped you to get like some insights, how to set the configurations, how it influenced um, the partition distribution and the number of partitions. And then in the next 1 or 2 sessions, we gonna deep dive onto the parameter which you usually use. So this is max partition bytes, or here we call it now megabytes. And the other parameter, which is also sometimes used, is the open cost. So we're gonna see already as a sneak peek that open cost doesn't really have the biggest influence, except if you have a lot of small files. So stay tuned for the next session. Feel free to subscribe below, and see you in the next episode.